And actually, while talking about sequencing, I mean, we are actually far behind compared to many of the experts here. It was only like 2 weeks ago that I first started to look at any whole genome sequencing data of Icelanders. But hopefully, we are moving fast. We are hoping that by the end of this month, we may have 100 people sequence 10x. But now, at this particular moment, there's really a lot that we don't know. And indeed, to me, the biggest challenge is really, I'm quite sure there are many important challenges that I don't know about them. And so, well, as I look more at the data, I will know. But actually, I mean, even what we know, there are obviously, essentially an infinite number of statistical problems, interesting ones. And one challenge to us, and I guess to any other research group, is to pick the right problems to solve. And for example, in our case, I would like to convince you that given the background data we have, we will probably be very good in identifying sequence calling problems and in evaluating the performance of different calling methods. But we will be very happy if other people will solve the technical problems to sequence calling, like a number of the speakers talked about yesterday. So now we do have certain advantages, and one main advantage we have is the work that we did in the last couple of years. So we first figured out a way to basically phase long haplotypes very accurately, and then a few months ago we finally published this paper in Nature that basically we're able to determine parental origins of alleles. So essentially, what we have now is very simple. We have 40,000 Icelanders who are typed with an Illumina chip. Most of them are the 300K, some are higher. And we are able to assign parental origins to over 97% of the heterozygous genotypes with 99.6% accuracy. So with parental origins, I mean, the parental origin, of course, is by itself interesting. But basically, when you have parental origins, you have essentially phased the whole genome. So now when you look at people, basically we have the paternal genome of a person and the maternal genome of a person. So it's basically now we are in the haploid genome situation. So now this is one thing that is related to something that Richard talked about this morning. So now, because we have these 40,000 people nearly completely phased, we have separated the paternal and the maternal genome. So we say, imagine, I take 2,000 Icelanders. So of course I imagine, essentially, let's say I'm sequencing them or whatever. But in this case, I'm doing a very simple thing. Right? I have 2,000 Icelanders. I basically means I have 4,000 haplogenomes. Then I randomly take an Icelander and try to reconstruct the genome of this random drawn Icelander. Of course, this is randomly from one of those 40,000, and try to create it as a mosaic of the 4,000 haploid genomes that I have. But then I can use different criterion. So even if I use a criterion, I'm only allowed to use pieces that are 10 centimorgan or more. And 10 centimorgan, I think the centimorgan is a more natural scale here. But of course, approximately, you can think of 1 centimorgan as corresponding to 1 megabase. So with 2,000 Icelanders, we can actually take a random Icelander. We can actually reconstruct 62% of the genome. Using, if you are only allowing to chunks that share, if you like, IBS 10 centimorgan. So this is like a sharing, assuming it is IBD, is a very, very long chunk. Well, first it's IBS, but because it is such a long chunk, it means that it's very likely to be IBD. And furthermore, if it is IBD, and I use IBD as the way that Richard used it, if it is IBD because it is so big, it means that the common ancestor is not too long ago. That means that the chance that mutations have happened between the two people is small. then it means that if you actually have the sequence from one of these sequence Iceland, and assuming your sequence is perfect and so on, then you can basically paste the thing into these other people who only have SNP type, right? So that's why this is directly related to imputations, okay? And you can see, I mean, okay, but there's only 62%. But if you go down to 5 centimorgan, it's still very big. It's go to 81%. And 3 centimorgan is 88%, and then 2 centimorgan is 91%, and 1 centimorgan is 95%. Actually, a lot of imputations are actually based on something that is around 1 centimorgan. Okay? And now, well, but if let's say we can only afford to sequence 1,000 Icelanders, then of course these numbers go down a little bit, but it's still like, well, you go to 2 or 3 centimorgan, it's still rather big. And indeed, even if you go to 500 Icelanders, well, if you go to 3 centimorgan, it's now 66%. Basically, you go from here to here. But if you go to 1 centimorgan, it's still pretty good. Of course, I also put in the corresponding numbers for if I imagine I'm taking a random CEU, right? Okay, so this allows us to do a number of things. So this again is based on very preliminary whole genome resequencing data, and actually called using standard methods. I think we've used Rich's method. So now I say, well, I can estimate heterozygote undercourse by studying discordant homozygotes between 2 individuals known to share one haplotype, IBD. Because I have all these phase things, I can easily pull out people or regions of people for a pair of people where they share a long haplotype, at least IBS. Then I can check, because if they do share a haplotype, then they are not supposed to have discordant homozygote, apart from, of course, mutations, right? And of course, what if we do, of course, there are quite a bit of discordant homozygotes. And those, of course, we think of as most of them are basically heterozygote undercourse, right? Many of them probably should be heterozygote. But one nice thing is, like, it is clear that those undercourse are very strongly associated with low threat score. So, of course, we would like to do something much more sophisticated, but even if we do a very simple thing, just use like threat score to filter, of course, we will lose yield, but we can actually get the error rate, or at least really bring the discordant homozygote down to very, very low percentage if we are willing to sacrifice some yield. Now, the other part is we can also estimate heterozygote overcourse. So now, because of our individuals, I mean, Iceland, of course, is really not an inbred population, but indeed people are related. So because the parents are related, so of course the people in general will have some homozygote chunks in the genome. So again, by studying individuals who are homozygotes for long stretch, 3 centimorgan, 5 centimorgan, whatever you think of as long enough, based on the chip SNPs, then you can look at from the sequence code the number of heterozygote sequence calls. Okay, so I looked at just this raw data, and it was much higher than I expected, because I learned from this X thing. This data is 15X. Well, the heterozygote overcall should be the percentage is supposed to be very low, as I understand. But if I just look at this raw data, it's much higher than what I expected. And again, but moreover, unlike these cannot, many of them cannot be filtered out using threat score. I mean, some of them have incredibly high threat score. And close examination actually reveals that some of these sequence SNPs are called heterozygote for everybody. So this is the type of artifacts that Phil talked about. Of course, everybody in our case is actually only 8 people. But, well, there's an example. There's a 60 kilobase region in the genome. There are nearly 1,000 sequence SNPs that behave like this. Okay? And I think, at least, I don't know about the latest release of the 1,000 genome data, but if you look at some of the earlier releases, it's quite clear that this problem is not as striking, but it's sort of there also in the 1,000 genome data. Okay? So this is the example that shows, like, addresses question of imputation, accuracy, methods, population, whatever. So we are interested in imputing, here in particular, low frequency variance. So it happened that on the Illumina chip, there are 13 variants that are below 1% in the isentic population. So we have 40,000 samples. Okay, so we artificially create a reference set. Okay, that we usually think of, and also is experience of others. If you have 10 copies of the variant in the reference panel, usually the imputation would be pretty good. Of course, it fluctuates, right? So this is what we did, okay, using our method. And then this is what you get from impute2. This is using the default setting. This is increasing the parameters. So of course, I mean, even increasing is going to 80, and based on Jonathan's talk, it's maybe there's quite a bit more improvement if we actually go to 500. Okay. But now again, the settings here, these three, is exactly the same. The same people, the same reference set, the same data, the same people they're imputing into. The only difference, right, is we are imputing, in our case, we are imputing into haploid data because we have the data pre-phased. Okay? But impute2, we are like, we just feed the thing into the thing without feeding it the pre-phased data. So the impute2, of course, is handling a much more difficult problem because you have to do all the phasing, whatever. Okay? So, but because of that, you can also say, so first, having pre-phased data, you can see the time gain here. So like this is about like, well, this is 30 times slower, and this is like 100 times, right? So time is actually quite important. I'll come back to this. But now if you just look at accuracy, and also we do have better accuracy, and it's really better for every SNP. I think it's only one tie. Okay? This SNP, for some reason, is always 0.987. Okay? So, but we are better, apart from time. Having the pre-phase thing do give us a little bit more accuracy. And well, I have to say, for rare variants, I mean, this is R square. And usually for rare variants, such a high R square actually corresponds to very low error rate. And in any case, R square is, in some sense, correspond to effective sample size anyway, right? So now, but on still, you can say, well, sure, you have some improvement here. 0.916 to, let's say, compared to this, 0.868. It's a few percent improvement. Sure, we would like to have it, but that, well, it's not a big deal. Okay? I mean, yes, in some way it may not be a big deal, but it's very, very interesting if you look at it a different way. Because if instead of having 10 copies in the reference panel, we only have 5 copies. So that corresponds to something like our we are sequencing half the number of people, right? Okay, and the thing, of course, drops. And actually, when you look drop, if you look at this individual thing, even the average drop, most of the SNP basically doesn't really matter. It is just, I think it's just one SNP that makes all the difference. It's like this one that go from 0.588, if you like, from 5 to 10. Okay. Many of these other ones are just very similar. In some cases, they can even be a touch better. Well, now if you look at that, even if we go to 5 copies, we still have 0.882, which is actually still higher than this. So you can argue, by having pre-phased data, we have saved more than 50% of sequencing costs because we can sequence 1/2 of the people and get better accuracy, right? Or at least you can argue that. Okay. So, but accuracy is important, but speed is very important too. Indeed, we have actually used the 1,000 genome data to impute all our samples. And one nice thing in our case is it's not just the imputation, it's because we have all the haplotypes with parental origin. So when we are imputing the thing, it's automatically the parental origin is also imputed. So we actually have performed all these analyses with and without taking parental origin into account. And we have performed association analysis for many traits. And there are actually quite a number of very promising results that we are following up. Okay, so now the example I showed you is like, well, these Illumina SNPs sure looks good, who cares? So let's look at something more real, right? So this is bracket 2. So bracket 2, well, that bracket 2 is the type of thing that everybody wants to find, right? Low frequency. So in Iceland, the carrier frequency is about 0.8 to 0.9%. It means the allele frequency is about one half of this, right? About 0.5%. Okay. So now this is what I call like unsupervised tagging. This is sort of like, even let's say I pretend I don't even know bracket 2 exists. Okay. I just take a 1 centimorgan haplotype in that region, and these are all common SNPs, but the 64 SNP in that general region, and that actually is very, very robust. I mean, it's not like a very specific like 64 SNPs, okay? And we found this SNP. Of course, we are trying to find finding a haplotype that tags the bracket 2, and this is the 2x2 table, okay? So these are the people who don't have the haplotype, don't have bracket 2. These are the ones that have both. Okay. So now these are the ones that are, if you think of it as tagging, then these are tagging errors. But then these tagging things are actually very, very interesting. So first, this 7, you can think of it as false negative. But actually, I have no doubt that 2 of them is not false positive. There's no way that the person who have that SNP haplotype have the bracket thing. Well, who knows? It can be some type of sample mix-up or whatever. So 2 of them is just some other problems. It's not the problem with the tagging. 5 of them are genuinely a tagging problem, because when we look at that, it's very, very clear. I mean, those people who have they don't have the mutation, they just don't have the full 1 centimorgan haplotype. They actually, it's just because they're close by recombination, but they actually can be extended quite a bit more on the other side. But this 25 is actually even more interesting. So these 25 are, if you like, false positive. They have the haplotype, but they don't have the mutation. Okay? At first, I thought, well, those are just, well, some type of errors, or maybe it's the bracket. No, those 25 are, with respect to the SNPs, they have the 1 centimorgan haplotype, but yes, it's quite clear that yes, they do not have the mutation. Because these 25 happen to be even more related, so to speak, to each other than these 169, because they not only share 1 centimorgan region, they share even more extended region. They share like a 3 centimorgan region. Okay, so there are 2 possibilities, right? One is they basically correspond to the background where the mutation exists, so they don't have the mutation, but then some drift, they actually becomes even more rare. Another possibility is although they look like they have the same 1 centimorgan haplotype, IBS, but maybe it's actually not IBD, because it could have like a recombination happens. And of course, when we have the sequence data, we may be able to figure out which one is which, right? So, but now if I have this reference set, there's another 20,000 people who have SNP type, but not directly bracket type. So now, if I use this as a reference set, I'm sure if I impute into this and other 20,000, I can impute it with very, very low error rate. R square, I have no doubt, is at least 0.95. Okay? And but now it's because you need to take care of these. So you do need to have, if you do that, you need to do the imputation using SNPs that are covering more than 3 centimorgan, because you need that to distinguish these from these. I mean, so going back to this this tagging thing, right? This tagging thing is very, very important. It basically means that if you have the SNP data now, if you somehow didn't know about bracket 2, there's absolutely no problem, and bracket 2 will jump out. Because any type of like local haplotype analysis, I mean, the p-value is so significant, it will jump out. So it means that if this type of thing exists in Iceland, we actually would have detected the signal even before the sequence data. And we have done something like that by sort of like looking at long haplotypes, and we have found such signals, and it's replicated, so there's absolutely no doubt that we have something, but we are now just waiting for the sequence data for us to figure out what is the causal variant, which can end up to be not necessarily easy, but we already have like locations that we know they are low frequency variant that have high effect. that are tagged by some haplotype. So actually, this is actually getting very close to the end of my talk. So this is like a general, I think it's going to be a general statistical challenge as more and more of this data correlated. Right? So here I talk about imputation, right? But this whole thing actually does not just apply to imputation. The whole thing is have to do with like everything that we do here, there's a lot of uncertainty, and then there's a lot of sampling model. And then the dependency, but then there's the dependency structure. And the dependency structure can get to be very, very complicated. But here it's just using imputation as an example of the structure, if I call it the correlation structure of the uncertainties, right? So because, well, you see this imputation, all the imputation programs, including ours, like actually the imputation is not a single genotype. We actually have a distribution. So in our case, it's actually we actually have on each strand we are not a free genotype. We are actually, because we are parental origin, we actually have probability for each the paternal allele and the maternal allele, right? But still, that is just, even let's say, first I have to say those probabilities are actually not really real probabilities in some sense, but well, if you like to believe they are, then they are. But even if they are good probabilities in some sense, first, even if they are good, you have to define it. Probabilities are always conditional. It's actually very difficult for you to tell me exactly that imputed probability, exactly what how it is depending on. Okay? But still, assuming that probability is exactly what you want for that genotype, it's only the marginal uncertainty that you are capturing from that distribution or from that probability. So obviously, you have within-person correlation. Like, I mean, the uncertainties associated with imputations of close bivariance, based on LD and so on, are obviously correlated. And even more, maybe potentially problematic is between individuals correlation, because two people sharing a long chip SNP haplotype, right? If you have uncertainties associated with whether they carry a rare variant, right? If let's say you decide it's 50% that one of them carry the variant and the other one is also 50%, but then it's most likely it's not like two independent flips of the coin, right? It's nearly just one flip of the coin, and it's either both have it or both don't, right? But some of the analysis that we are performing now, just using the imputed ones, may not take these correlation structure into account. And most of the time, it may not be a big problem, but sometimes it might. And I generally, at this point, actually do not really know so how often, if at all, it will come up to be a severe problem. But you know in general that there's something that you should also keep in mind, right? And one thing I certainly know, I don't know like how extensive this problem is going to be, but certainly this type of problem is in general more severe for rare variants than for common variants. So the point is partly say, well, like a lot of the things have been done with common variants, and most of the time we have not seen like very serious problems. But that may sometimes just give you a false sense of security. When you're dealing with rare variants, like things are quite different. And because of the type of thing that we wanted to do, this is the last slide, it is even more important for us to try to deal with those uncertainty in the right way. Because we are not just doing this type of imputation, imputing sequence variant into people who already been chip typed. We are also trying to use the pedigree. So if these two people share a very long haplotype, and they are related like that, we are also imputed into these people that are completely untyped. And then we are also like trying to impute sort of what I call horizontally. These are what I call highly probabilistic imputations. So like, because some of these imputations, you can be close to sure, but this type of thing is a lot of uncertainty, but it can still give you some extra information. But if you really try to use these in the right way in the association analysis, you probably would have to be very careful about the correlation structure of the errors. So thank you very much.
Thank you. Questions? I will this time get in quickly with mine. Of course,
Okay.
you've got not only the short range correlation, due to sharing of the haplotype, you've got this kind of longer range that if you're sharing a long haplotype in this genomic region that you're looking at, you're probably sharing a lot genome-wide, and you've got correlation of phenotype due to polygenic causation, which is a sort of separate correlation issue to take into account.
Yes. So one type of thing is like I think actually Peter touched on this, right? Because actually I'm talking about the correlation structure of the imputation and accuracy.
Yes.
But actually, even if you don't have that accuracy, right? Because your samples are correlated, you still need to adjust for the people being related. And of course, we have been all using like some form of genomic control, right? But and it have been quite used, work quite well, right? But for the variants, just for that problem, we may again need to use some type of genomic control. But the genomic control can be a little bit more complicated than just using these common SNPs to figure out the
I think you'll probably need something more sophisticated. Anyway, anybody else got questions? No, expected more, but if there are none, then people must be hungry. So thank you very much to Augie and to all the speakers.